Imagine you've just returned from space. You've survived re-entry to the atmosphere at 17,000 miles per hour. You've landed a 200,000-pound glider with no engine, no second chances on a runway in the middle of the California desert. Now, NASA has to figure out how to get you home. Not back to Earth, you're already there, but home. To Florida, 3,000 miles away. Because here's the thing nobody mentions when they celebrate the Space Shuttle. The most sophisticated flying machine ever built couldn't fly itself across the country. And solving that problem required one of the most audacious engineering decisions in aviation history. Stick around to discover why NASA really had to redesign the 747 to save the Space Shuttle. Let's go back to the 1970s when NASA is designing the shuttle program. The concept was brilliant. Build a reusable spacecraft, launch it like a rocket, orbit the Earth, and land it like an aircraft. Use it again, and again, and again. That's the promise. Affordable, sustainable access to space. But here's where the first crack appears in that dream. The shuttle orbiter, officially called the orbiter vehicle, was by any measure enormous. 122 feet long, a wingspan of 78 feet, standing nearly 57 feet tall and fully loaded, weighing in at around 240,000 pounds at launch. It was designed with only one job in mind during re-entry: to glide, no engines, no thrust, one shot at the runway. And for most of the program, that runway was at Edwards Air Force Base in California, a wide open lake bed, a forgiving surface. Ideal for an unpowered vehicle feeling its way down from 300 miles above Earth. But the launch pad? That's at Kennedy Space Center in Cape Canaveral, Florida. The shuttle would land in California, need refurbishment, and then have to make it back to Florida for the next launch. A journey of roughly 2,500 miles. In a vehicle with no engine capable of sustained atmospheric flight. NASA had essentially built the world's most expensive glider, and now they had to move it across a continent. You might be thinking, just drive it by road. But let me stop you right there. A 78-foot wingspan, that's wider than a 4-lane highway. The vertical stabilizer, the tall tail fin, stands well over 50 feet high. There are bridges, overpasses, power lines and tunnels everywhere between California and Florida. You'd be looking at months of road closures, utility relocations, and probably dismantling parts of the orbiter that are specifically not designed to be dismantled for every single journey. And even if you somehow managed all of that, those heat shield tiles on the underside, 24,000 individual ceramic tiles, some as thin as an inch, are extraordinarily fragile. A single vibration, a rough patch of asphalt, and you're replacing expensive tiles for weeks. So road transport was a non-starter. What about rail? Same problem. Rail tunnels in the American West were not built with a 78-foot wide spacecraft in mind. And the loading gauge, the clearance envelope for railroad equipment, makes the idea essentially impossible without a purpose-built track running coast to coast. By sea? A barge from California around the tip of Florida, up to the Cape. That's nearly 5,000 miles of ocean exposure. Salt air attacking those tiles, weather windows, time lost. NASA needed its orbiters back in processing quickly to maintain any hope of that ambitious launch schedule. None of it worked. There was really only one option left: fly it. But not under its own power, obviously, as the shuttle orbiter had no jet engines. Its main engines burned liquid hydrogen and liquid oxygen, not exactly a combination you fire up for a cross-country ferry flight. What NASA needed was a mothership. A flying platform large enough, strong enough, and powerful enough to carry a 170,000-pound orbiter. That's the weight in ferry configuration without main engines installed and largely drained of fluids, strapped to its back through the skies of America. And when the engineers started looking around at what actually existed, only one aircraft kept coming up. The mighty Boeing 747, Queen of the Skies. Introduced in 1969, it had 4 engines and was capable of lifting over 800,000 pounds at max takeoff weight. a fuselage so wide that the Wright brothers' entire first flight could have taken place inside it. The 747 wasn't just the biggest airliner in the world, it was the only aircraft in existence that was even remotely close to being able to do this job. NASA purchased 2 of them, and then they proceeded to completely transform them. Here's where it gets deeply interesting. You can't just bolt a space shuttle to a 747 and call it a day. The aerodynamic consequences alone would have been catastrophic. First, the mounting system. The orbiter attaches to the 747, designated the Shuttle Carrier Aircraft, or SCA, via a system of 3 struts. 1 attachment point forward, 2 points aft, specifically designed to handle the load distribution and stress transfer from an orbiter that weighs as much as a loaded semi-truck. Now think about what happens aerodynamically when you put something that large on top of a wing. The orbiter sits directly behind the cockpit and over the wing. Its body disrupts the airflow over the entire aircraft. And critically, it creates enormous yaw instability, a tendency for the whole stack to want to rotate sideways, like trying to drive a truck with a giant sail mounted on the roof. To counter this, Boeing's engineers added 2 additional vertical stabilizers to the tail of the 747. These fins, one on each side of the existing horizontal stabilizer, were purely for yaw stability. Not pitch control, but yaw. The aircraft needed to resist the constant side force generated by the orbiter's massive cross-section pushing through the air. The elevators were also modified to give the pilots additional pitch authority, because with that much weight and drag above the fuselage, the standard control surfaces weren't enough. The performance numbers tell the story better than anything else. A standard 747 cruises at around 35,000 feet and 560 miles per hour. The SCA with an orbiter on its back was limited to roughly 13,000 to 15,000 feet and about 300 miles per hour. Range dropped significantly, requiring multiple fuel stops on cross-country flights. The crew described handling characteristics that felt, at best, like flying through wet concrete. Sluggish, heavy, every input demanding enormous respect. One pilot described it as flying 2 aircraft simultaneously, except one of them was above you and had no interest in cooperating. Here's something interesting that many people skip entirely when looking at this monstrous task. How do you actually get a 122-foot spacecraft on top of a 747 in the first place? The answer is a specialized piece of ground equipment called the Mate-Demate device, or MDD. NASA had 2 of them, one at Edwards Air Force Base and one at Kennedy Space Center. The MDD was essentially a massive steel gantry, a structural framework tall enough to straddle both the 747 and the orbiter simultaneously. The orbiter would be rolled underneath it, lifted by slings attached to the gantry's hoisting system, and raised high enough for the 747 to taxi directly underneath. The 747 would then be carefully positioned, and the orbiter would be lowered onto the 3 attach points with millimeter precision. The whole process took hours and required a ground crew operating with the kind of focus you'd expect from, well, people who work with spaceships. At locations that didn't have an MDD, and remember, emergency landings could have put the orbiter almost anywhere, NASA had a mobile crane system capable of performing the same operation in the field. It was never simple, but it worked every single time. The first captive flight of the SCA, carrying the prototype orbiter, Enterprise, took place on the 18th of February 1977 from Edwards Air Force Base. That was purely a test of how the combined stack handled in the air, no separation, just flying together. The results were concerning enough to keep the engineers busy for many more months, but they solved it. Eventually, the SCA became a routine part of the shuttle program. Over the 30-year life of the program, the 2 aircraft, NASA 905 and NASA 911, flew 223 ferry missions. Those flights led to some of the most surreal images in aviation history. A space shuttle riding on top of a 747, banking slowly over the Hudson River past Manhattan, over the National Mall in Washington, D.C., over the Golden Gate Bridge. Those retirement tour flights in 2012 brought millions of people out onto rooftops, bridges, and sidewalks to witness something that their eyes kept telling them was wrong. That is not how things are supposed to look. And that reaction? That instinctive disbelief? That's the measure of what NASA actually pulled off. Here's what strikes me every time I look at those images. The Space Shuttle program is often critiqued, fairly in many ways, for not living up to its original promise of cheap, frequent access to space. The flights were expensive, the turnaround was long, the safety record had 2 catastrophic failures. But when you look at the shuttle carrier aircraft, you see something different. You see engineers who were handed an impossible logistics problem. Move a vehicle the size of a small airliner covered in fragile ceramic tiles across a continent, repeatedly, safely, on a reasonable timeline and with only 70s technology, and who solved it not by giving up or accepting limitation, but by picking up one of the greatest airliners ever built and redesigning it from the inside out. They added fins. They reinforced frames. They built a gantry the size of a building. They restricted an aircraft that could cross the Atlantic to puttering along at 15,000 feet at half its normal speed. And they made it work for 30 years without a single loss. That's not a footnote in aviation history. That's a true success story. If you enjoyed this video, hit subscribe to ensure you don't miss our future uploads, and I think you might love watching this one next.